So in the previous video we looked at collision theory. Collision theory talks about what is happening on a molecular level that controls the rate of a reaction. We can also look to the molecular level to explain why a reaction occurs or how that reaction occurs as a step-by-step process. How do those individual reactant molecules turn into product molecules? And to do that we look at something called a reaction mechanism, which literally looks at the series of collisions that take place that allow the reactants to become products. So a mechanism can have one step or more than one step. Each step in the mechanism is called an elementary step. So in the mechanism I have one or more elementary steps. And when I look at a mechanism, the mechanism must satisfy two conditions. So this is the first condition. It must account for the experimentally determined rate law. So really the rate law for the overall reaction comes from the mechanism or can be explained by the mechanism. And then the second one, where it must be consistent, that simply means when I take the steps of my mechanism and add them together, I get the overall reaction that I observe in the lab. So here's an example of a reaction mechanism. First, I have my overall reaction, and this is the reaction you looked at last time when you were looking at the actual collision theory video. This mechanism is a two-step mechanism. So what this says is the first elementary step, two nitrogen dioxide molecules collide to form these two products. Then a carbon monoxide molecule collides with this NO3 that is formed in the first step to form the CO2. So each of these steps is an elementary step. When I add them together, it gives me the overall reaction. So this product of the first step, NO3, nitrogen trioxide, which is used up in a subsequent step, is called a reaction intermediate. So it's something that exists in the process of the reactants becoming products, but does not appear in the overall reaction. So when I look at the stoichiometry, what has to happen in my mechanism is that any reaction intermediates must end up being used up by the time I get to the last step of the reaction, so that the overall reaction matches the one I observe in the lab. So when we're looking at each step, we can describe each step's molecularity, and that simply refers to how many molecules are involved on the reactant side of each step. So if I have a single reactant that splits apart, the molecularity is unimolecular, one molecule. If in my elementary step I have two molecules colliding, that would be bimolecular. And if I have three molecules colliding, that would be called termolecular. So if I look back at this mechanism, I can see that each step involves two molecules colliding with each other. So each of these steps individually would be bimolecular. So here's a little chart that shows the molecularity of each step. And as it turns out, the rate law for an individual step can be determined by looking at the stoichiometry of the step. So for example, if in a step A plus B gives me products, so that means a molecule of A collides with a molecule of B, the rate law is K times the concentration of A to the first power times the concentration of B to the first power. So I can actually look at these coefficients to give me the order of the reactants if and only if it is an elementary step in a mechanism. So if we look at this where I have two A molecules colliding, I can see that my order is 2 because that would be 2A. And down here in this termolecular step, you can see the orders match the coefficients. But again, that is true only because this is a step in the mechanism and not an overall reaction itself. Okay, so if we take a look at reaction mechanisms, if I have a one-step mechanism, since this is the overall reaction and it is the only step in the mechanism, so this is an elementary step and it is an overall reaction, then I can write a rate law based on the coefficients. So any one-step mechanism, the coefficients are going to be your orders. Only for a one-step mechanism, because in a one-step mechanism, again, this overall reaction is also the elementary step in the mechanism. If I have a two-step mechanism, what we find is that one of the steps is always going to be the slowest step. So if you're looking at a mechanism, this is called the slow step. So the slow step is referred to as the rate determining step. That means that the reaction can only proceed as fast as this first reaction proceeds, because as soon as I produce that NO3, it's going to be immediately consumed in this faster step. So the rate law for this slow step is equal to K times the concentration of NO2 squared. So since this slow step is the rate determining step, the rate law for the slow step is the rate law for the overall reaction. So this would be the rate law for the overall reaction. And so that's what we mean when we say that the mechanism must account for the experimentally determined rate law. So in order for this to be a valid two-step mechanism for this overall reaction, I must observe an experimental rate law that looks like this. If the rate law is different, then this is not a good mechanism. So let's take a look at what an energy diagram looks like when we start thinking about multi-steps. Typically, the energy diagrams you're used to seeing just have one hill. And that one hill, the peak where the activated complex is, corresponds to the energy of the slowest step, because the step that has the highest activation energy is going to be the slow step of the mechanism. So if we were just looking at an overall reaction, we would just see this big curve. In a reaction that has three steps, the slow step is going to have the highest activation energy, and that will be the rate determining step, and that will be the step that gives you the rate law for the reaction. Okay, so let's take a look at a problem. So here we have an overall reaction. Here we have an experimentally determined rate law. So these are things I observe in the lab. And here is a possible mechanism. So, is this an acceptable mechanism? So the first thing I need to do is add these two reactions together, these two elementary steps, and figure out, does this mechanism give me that overall reaction? So NO2 plus F2 plus F plus NO2. So there are all my reactants on my reactant side, and on the product side I have NO2F plus F plus NO2F. So now if I cross out things that appear on both sides, in this case the fluorine atom, that goes away. This would be a reaction intermediate, and what I have left is two NO2s and one F2 on this side, and on this side I get two NO2F. So that looks the same as the reaction I see in the lab, so that's good. And then the next thing I want to do is write the rate law for the slow step. So here we go. Here's the slow step. The rate of this step is equal to K times the concentration of NO to the first power times the concentration of F2 to the first power. And I know the order of each of those is 1 because this is an elementary step and there's a 1 and a 1. Okay, so this rate law for the slow step matches the experimentally determined rate law, so this is a possible mechanism. And that's as much as we can say, that it is a possible mechanism. You don't know for sure because you could come up with all kinds of other combinations of collisions that give you the same overall reaction and give you the same overall rate law. So this is just one possibility for a mechanism, but that would work. Okay. So now, if I'm looking at this mechanism, here is my overall reaction. Oh, and there's an arrow missing. There should be an arrow right there. Here's my overall reaction. If I write the rate law for the slow step of this reaction, it would be rate. Here, I'm going to write it down here. So for the slow step, rate equals K times the concentration of NoCl2 times the concentration of NO. Now if I look at that rate law, I could never observe this rate law in the lab because NoCl2 is a reaction intermediate. It does not appear in the overall equation. So at first glance, you might think that this mechanism is not a good mechanism for this overall reaction. But you'll notice something different about this reaction. In the fast step, instead of having a left to right arrow, I have a double-headed arrow. That double-headed arrow means that the reverse reaction can also occur and is occurring at the same rate as the forward reaction. So if you think back to the simulation, when you had that single molecule, the first time you fire it, bouncing back and forth, and it turns into products and turns back into reactants and back into products and back into reactants. That's what's happening here. So the rate in this direction is the same as the rate of the reverse reaction. They are happening at the same speed. So if I look at this fast step, I can see that one rate law